Welcome to day 3 of gas laws. Today we're gonna add the last couple laws in and clean stuff up a little bit. So we're gonna start here. Write all of the proportionalities that we wrote last class. So pause that, see if you can do it. So we said that pressure was inversely proportional to volume. We said that pressure was directly proportional to temperature. And we said volume was directly proportional to temperature. Okay? So this one I'm going to rearrange. I'm going to say the pressure times the volume is directly proportional to something. 1. Okay? It's directly proportional to a constant. So I want you to pause and try to combine all of these to make one law, which we call the combined gas law. So you'll notice that pressure times the volume should be directly proportional to the temperature. This has all the relationships that we need. The pressure is inversely proportional to the volume. If one goes up, the other one goes down. And it has pressure is directly proportional to temperature, and volume is directly proportional to temperature. Okay? Now, if you got this far, see if you can turn this into a law. The way you're going to do this is you're going to you're going to change this proportionality to an equality. PV equals KT. And then you're going to isolate the constant like we did last time. Divide both sides by T. And then you can say P1 V1 over T1 equals K, which equals P2 V2 over T2. All right, and this is a combination of all the gas laws, and not surprisingly, we called it the combined gas law. Okay, so let's see what a problem with combined gas law would look like. So while I'm looking through here, I'll notice that there's rather a lot of stuff going on, okay? The volume of a gas at 27 degrees and 0.200 atmospheres is 80 milliliters. What volume will the same gas sample occupy at standard conditions? All right, well, here's my initial temperature. Here's my initial pressure, and here is my initial volume. Okay, volume's what I'm trying to find. Volume 2 is what I'm trying to find. Under standard conditions, so this is standard temperature and pressure, which means that this is P2 and T2. Okay, so because I have everything changing, I'm going to do the combined gas law. P1 V1 over T1 equals P2 V2 over T2. And then I'm trying to isolate V2. That's what I'm trying to solve for. So I'm going to multiply both sides by T2 to cancel this T2, divided by P2 in order to cancel this one. I'll do that on both sides. These cancel, and I get V2 equals P1 V1 over T1 times T2 over P2. And then I can just start plugging numbers in. P1 is 0.200 ATM. V1 is 80 milliliters. T2 is standard temperature, which is 0 degrees Celsius, or 273.15 Kelvin. T1 is 27 degrees Celsius, which is 300.15 Kelvin. And P2 is standard pressure, which is 1 atmosphere. Okay? So everything has three significant figures. This one atmosphere, that's a definition, so that's exact. So this has 3 sig figs, this has 3 sig figs, this has 4, this has 4. So we have, our answer should have 3 sig figs. When I calculate it, I get 14.6 milliliters. Okay? So that's doing calculations using the combined gas law. The final kind of smaller law that we're going to talk about is Avogadro's law. Okay? And we're going to use the same plunger that we had before so that pressure is constant. Okay? Meaning the P out outside here, okay, equals P in here. Okay? So the syringe can move up and down so that the pressure outside is equal to the pressure inside. Okay? So now Avogadro's law relates the number of moles to the volume of a gas. All right? So let's think about how that works. If I have a sample of gas in here and the pressure outside is going to be constant, it's going to be equal to the pressure inside. Okay? If I add gas particles, okay, you would have more collisions, which means you should get more pressure, but P in has to equal P out, and P out's not changing. So the volume is going to increase in order to equalize the pressure. All right? So that is, if you increase the number of moles, then the volume is going to increase. All right? Another great example of this is a balloon, right? If you blow into a balloon, you're adding more gas particles, and the pressure inside the balloon is roughly equal to the pressure outside, okay? And so the volume increases. So that tells you that volume is directly proportional to the number of moles, okay? So we could take this all the way into we could go V equals Kn, and then we could do V1 over N1 equals V2 over N2, okay? But really, we just kind of stick with this proportionality, okay? So the interesting thing about this is now we can say that pressure times volume is going to be proportional to the number of moles times the temperature. All right, and if I add a constant, this constant is actually special. This constant is always constant. All right? So, why is that cool? Well, we can solve for it. So if we solve for K, pressure over volume, pressure times volume divided by the number of moles times the temperature gives you this constant K. All right? And let's just pick some values that make sense. Well, for pressure and temperature, we'll just use standard temperature and pressure. Okay? Now, one of the things that Avogadro did, this law up here, by the way, is called Avogadro's law. One of the things that Avogadro determined is that no matter what gas you had, if you had exactly 1 mole of the gas, you always had the same volume. That's really cool. And the values for that were 1 mole of gas equals 22.4 liters of gas. All right. So if I set this up, my pressure as 1 atmosphere, okay, my volume as 22.4 liters of gas over the number of moles of gas, which is 1 mole, times the temperature, standard temperature, 273.15 Kelvin. Okay? If you do this calculation, you get something very close to 0.0821, and then our units are kind of a mess. The units are liters times atmospheres per moles times Kelvin. And I told you that this is always a constant. Okay? This K, it's always a constant. And as such, they didn't stick with K for constant. They gave it a capital R. Okay? So, this equation up here, PV equals KNT, becomes PV equals nRT. Boom. This is called the ideal gas law, which makes this the ideal gas constant. Okay? We're going to do lots of calculations with ideal gas law and the ideal gas constant, and they're a little unusual. So let's take a look at a sample problem. All right. One of the ways that you can clearly identify a ideal gas law problem versus one of the other laws is that in an ideal gas law problem, everything stays the same. Okay? It's not you have a sample of gas and you're changing the conditions on the gas. It's just you have a gas under one set of conditions and you're trying to determine something about that gas. So let's take a look at this problem. I have a 2.07 liter cylinder containing 2.88 moles of helium gas. So it's helium gas at 22 degrees Celsius. What is the pressure in atmospheres of the gas in the cylinder? All right, so here's my volume, okay, because the gas is going to expand to fill the cylinder. So this is my volume. Here are my number of moles, okay, and here's my temperature. And what I'm trying to find here is the pressure. Okay, so if you look, this is basically set up to be the ideal gas law, PV equals nRT, where I'm going to solve for pressure. So I'm going to divide both sides by volume. Okay, so pressure equals nRT over V. Now, the units for R are kind of a mess. So I usually recommend doing R either first or last. Okay, remember this is multiplication and division, so order doesn't really matter that much. So I'm going to put it first. Okay. And I'm going to say it's 0.0821 liters times atmospheres over moles times Kelvin. Okay. Then I'm going to say that there are 2.88 moles. Okay. That's my N. And then my T is this 22 degrees Celsius, which is 295.15 Kelvin. And I take all of this and I divide by the volume, which is 2.07 liters. Okay, now I'm going to stop here and check my units. Check your units. So liters cancel, moles cancel, Kelvin cancels, and I'm left with units of atmospheres, which is a unit of pressure. Yay! All right, when I do the calculation, I'm going to use 3 significant figures. These both have 3. All right, and I get 33.7 atmospheres. There's your answer.